In the last class we talked about electromechanical analogies, in particular for the three fundamental mechanical elements, namely mass, spring and the damper. We were able to formulate both the transfer matrix as well as the equivalent electrical circuit. For the mass element, we understood that the forces on the two sides need not be the same, whereas the velocities on the input and the output side has got to be the same. Accordingly, we obtained the impedance for the mass to be I omega m. For the spring element, we obtained the equivalent electrical circuit to be an element of impedance ZS, which is placed in parallel in this fashion, and the transfer matrix was obtained in this way. Please note, we have defined capital C equals to compliance, which is just the reciprocal of the stiffness K. Okay. So, capital C is the compliance. And lastly, for the damping element also in a similar fashion, we understood that the force of the input and the output port in a damping element has to be the same. The velocities could differ. So, accordingly the velocities here are V2 and V1, and this could possibly be different. C in small alphabets denotes the damping coefficient, capital C denotes the compliance, but C in the small alphabet denotes the damping coefficient, and we were able to derive that the analogous electric circuit is also a parallel element of impedance ZR, which is related to the damping coefficient, and the transfer matrix was obtained in this fashion. Today we will look at how to assemble these fundamental elements in that were derived, and using these assembly of springs, masses and dampers, we should be able to construct any mechanical system, and accordingly we will define what is the electrical analogous circuit for this, and as also we will find out the transfer matrix appropriate to assemblage of such spring, mass and damper elements. Okay. So, what we will do firstly is to start with, we will take our very fundamental example of just a spring and a mass. So, this is example 1. So, as we know that for the mass element we will have an impedance of Zm. So, there is with reference to the ground line, there is a force on the mass, and that force is equivalent to a voltage in the electrical circuit terminology. So, this is what it represents for the mass element alone. Similarly, if we detach the spring element, so what we do is that we detach the two elements, the mass and the spring. So, the mass element corresponds to this electrical circuit, the spring element would correspond to this mechanical circuit, the electrical circuit corresponding to the spring mechanical element will be this, as has been derived in the previous class. Now, what we observe in this case is this output of the spring is basically at a fixed position, it is not allowed to move. So, this I will call this V0, this point is not allowed to move. So, that in turn implies that there is no current which can go in this part of the electric circuit. The output should not have any current. Now, the output cannot have current only if you will have a open circuit configuration here. So, this is basically an open circuit. In case we consider this part of the circuit to be open, which means we just leave the wires hanging loose, we do not connect it, right. That would be an open circuit, and that open circuit would essentially mean that the impedance is infinite for in circuit terminology, but in a more intuitive way we can understand that in this portion there is no current that will flow, because the circuit is left open, right. And the current being analogous to velocity, that also means that V0 is 0, which is exactly what we wanted. Now, next what we consider is that between the output port of the mass and the input port of the spring, the same forces has to get transmitted, which means the voltage between these two ends also has to be the same. So, this is the voltage which anyway has to remain same, and the other line here was the ground line. So, this could also be connected. As a result, what we have for this circuit is the following, that there is an impedance associated with the mass, the value of which is I omega m, and there is an impedance associated with the spring, which is basically in a shunt position, but then the other part which I am drawing it in red is basically needless to draw, because this part of the circuit is open, nothing happens here. So, you might as well not draw it, but then the voltage between the ground line and the one which is hitting the mass, if this is the ground line, this voltage is going to be effectively the force. Okay. So, this completes the electrical circuit for very simple fundamental mechanical system, that of a spring mass, right. Now, how does this boil down to in terms of the notations of the circuit? So, if you are required to find the velocity, which basically means the velocity at the input end of this mass, then as per the circuit theory we understand F by B will be equal to the equivalent impedance of this circuit, and since there are just two impedance Zm and Zs and they are in series here. So, that will be Zm plus Zs. So, F by V, that is the ratio of the force and velocity of the mass at its input end, is going to be Zm plus Zs, which by definition is again I times omega m minus k by omega, right. So, therefore, at omega equals to square root k by m, what will happen? At omega equals to square root k by m, we will see that Z equivalent is going to how much? 0, right. So, the impedance of this circuit is going to 0 at this condition, which basically has been obtained by setting omega m is equals to k by omega, and that in turn would mean omega square is k by m, right. So, at this frequency omega equals to square root k by m, we see that the impedance of the equivalent electrical circuit is going to 0. So, that means it is virtually short circuited, right. What happens when you have a short circuit in electrical terminology? With a certain potential difference, if you short circuit, large current will flow through, and large current essentially means large velocity of the mass point. So, that again boils down to our resonance idea, but here I am bringing the resonance idea from an electrical analogy rather than using the mechanical perspective. So, here what we see is that at ZE will become 0, and this would imply V is large for any non-zero F. This is the resonance condition, wherein you can have a large response of the structure even though the forces are very small, right. So, or in other words, the magnification from force to velocity is by a large amount. So, from here what we will realize is that the resonance is obtained when you have the imaginary part of impedance to be going to 0, right. So, I mean here the impedance is completely imaginary anyway, but later we will see that there is a possibility of damping also that will bring in the real part, but maybe I will hold that for a while. So, now for this very same system, that of a spring mass system, we will analyze the transfer matrix method. So, accordingly we have 3 stations which are defined as 0, 1 and 2 in this diagram. So, what we need to do is relate the forces and velocities between each of these successive stations. Between 0 and 1 we understand it is going to be a spring element. So, F0 V0 is going to be related through F1 V1 by a spring element, and the transfer matrix for that is going to be 1 0 1 by I omega 1 by Zs basically. This is going to be 1 by Zs and 1, where Zs is 1 by I omega s C, capital C. This is the transfer matrix relating the variables between station 0 and station 1. Now, in the next stage we need to relate the state variables from station 1 to station 2. Okay. So, we need to find out F2 V2 in terms of F1 V1, and that also is simple because that is just the transfer matrix associated with the mass element, that also was defined, and that transfer matrix is given by this form, where Zm is j omega m, right. So, therefore, it is trivial to find the transfer matrix relating station 2 to station 0, right. That will be the product of the two transfer matrices, which are given as 1 Zm 0 1 1 1 by Zs 0 1, and if you multiply them, what we get is the following: F2 V2 is given by 1 plus Zm by Zs, then we will have Zm, and we will have 1 by Zs, and finally, we will have 1 F1 V1 sorry F0 V0. So, this is the transfer matrix which relates the state variables between the upstream point and the downstream point. The downstream point is station 0 and the upstream point is station 1. Now, from the transfer matrix itself, again we can calculate what is known as the drive point impedance. By drive point impedance, what we mean is the following: we will have this spring and mass, this is mass and this is stiffness, it is being driven by a certain force, it has a certain velocity, and as per our notations, this velocity is denoted by V2 and the force is denoted by F2. So, the drive point impedance will be given by F2 by V2. Okay. And again, when this drive point impedance has shows a characteristics that it is nearly 0, then it will be associated with a resonance condition, right, because then even for a small force you will have large velocity of this mass, right. So, in this case obviously the impedance will be completely imaginary, as you can work it out, but the point is this: how do we calculate drive point impedance in this case? That is very simple. We have to realize that V0 has got to be 0 as per the problem, because the spring is fixed at one end. So, V0 has got to be 0, which means from the transfer matrix, as we can see, F2 is 1 plus Zm by Zs into F0, right, and V2 will have to be F0 by Zs. There is no need to consider the effect of V0 because V0 is 0. So, from here if we make the substitution here, we will get 1 plus Zm by Zs. Instead of F0 we might as well write Zs into V2, right. So, that implies F2 is equals to Zs plus Zm into V2, or drive point impedance F2 by V2 is equals to Zm plus Zs, which is exactly equal to the equivalent impedance of the electrical circuit. So, in this electrical circuit we have the equivalent impedance as Zm and Zs, and this F and this V is basically the input force and velocity that is being offered to the mass. So, therefore, the drive point impedance is the equivalent impedance in the electric circuit, and that can also be calculated using the transfer matrix method as shown above. So, I will leave you as an exercise, prove that if drive point impedance is 0, then we have a resonance condition. Exactly what we did for the circuit analogy. You just have to write the expressions for Zm and Zs in its entirety and multiply out those two terms, and then again Zm plus Zs basically is what we have written. So, it is almost a trivial exercise, you could as well do it by yourself. Next we will look at a second example. Actually, for the first example it is almost trivial, because if you start from the free body diagram and write the equations of this system, you could as well derive everything that you want from a completely mechanical perspective without going to this electrical analogy or transfer matrix or anything like that. But now the electrical analogy and the transfer matrix will become really handy when you think about a large group of interconnected springs and masses. So, the idea here will be very simple as opposed to our free body diagram approach. So, let us say you have as many as you can think springs and masses. Okay. The idea is just the same, start from the one which is closest to the fixed point. There has to be some fixed point, otherwise it is not a vibrating system, otherwise it is a dynamical system. So, I will call this K1 M1, I will call this K2 M2, I should have put the dotted line later. This is K2 and this is M2, and then things can continue for a while, and this is Kn Mn, and then this is Kn plus 1 Mn plus 1 and so on. Okay. Finally, let us say there is a force hitting this structure. Okay. So, then as we will now see, the analysis here is really simplified if you go by the electrical analogy or by the transfer matrix method. Remember, for this system when n is large, it is actually pretty cumbersome to do the free body diagram and write equations of equilibrium for each of these systems, or if you want to derive the Lagrangian form, that also could be a little more cumbersome, but in electrical analogy this will turn out to be really simple. So, let us start from the upstream point. The upstream point is a spring with stiffness K1. So, as we know, the impedance associated with the spring is in the shunt position. So, this is the impedance associated with the spring, right. Next is that there is a mass. So, mass will offer an impedance in electrical terminology which is in the inline position, and this line is always the ground line, right. Now, again the same arguments will go through, that is the output end of the spring is not supposed to have any velocity, which means there is not, in the analogous electrical circuit there cannot be any current in this branch, which can only happen if this circuit is left open. Okay. So, we are not going to close this circuit, it is going to left open, which means as well we might not consider this part of the circuit. Next, the force between the mass and the spring, the same force has to get transmitted, which means the voltage between these two ends must also be the same, which means we can as well connect it, right. And anyway these two are ground lines. So, there is nothing which prevents us to connect it, right. So, this idea will keep growing. So, we will have the next, for the next spring mass system also we will have another ZS2 and another ZM2 and so on. This will keep happening till the nth level, wherein we will have a impedance in the shunt position with the value of ZSN, and the inline impedance would be ZMN. Then followed by that the upstream point will have an impedance associated with the spring n plus 1. So, ZS n plus 1, okay. And then there is an inline impedance Zm n plus 1, and then finally this mass is seeing a force which is capital F. Force is analogous to velocity in the electric circuit theory. So, that force is analogous to voltage in the electric circuit theory, which means this point, the input point of the mass, will see now a voltage which is F, right. So, the circuit is fairly easy to draw. No matter how many springs and masses you give me, all that I need to do is just keep arranging the springs in the inline in the shunt position and the masses in the inline position and complete this circuit. Once this circuit is made, I can take it to a software such as Simulink and simulate this system without worrying about how the equations have been formulated, etc., etc. So, any harmonic excitation problem can be done in this fashion. Transfer matrix will be even simpler. So, associated with each of these blocks we have spring masses, we have formulated the transfer matrix, right. So, finally, if we need to understand what happens, I will call this, let us say F bar, and I am interested in what happens to this V bar, because I have lost the count of the number of stations. So, we will call this F bar and V bar. This F bar and V bar has got to be related to F0 and V0, which is happening at the input end. Anyway, V0 is 0, but none the same we will choose to write the transfer matrix in a general form, including the effect of V0, right. And then each of the transfer matrices starting from the upstream end need to be written one after the other, and the product has to be taken. We know that associated with each transfer matrix, associated with each of these spring mass system, the transfer matrix I have already derived as 1 plus Zm by Zs, 1 by Zs and Zm and 1, right. So, associated with the index we get an index 1 sitting over here, right. So, each spring mass block is going to give you a transfer matrix with that specific structure. All that you have to do is to keep multiplying these transfer matrix from downstream end to the upstream end, right. So, the generic form of the transfer matrix is this: 1 plus Zm1 Zs1, sorry, I will call this I, Zmi 1 by Zsi 1, and you will need to make a product of all these transfer matrices. I equals to 1 to n plus 1 in this case. There are n plus 1 such transfer matrices. You will have to make this product. So, the transfer matrix can be readily obtained as a matrix multiplication. That is actually no big deal. These are just 2 by 2 matrices. No matter how many matrices are there, you could almost do it in a pen and paper. You could write a simple code also to do these matrix calculations, multiplications in no big time, right. So, the point is, when you have such assembly of springs and masses, it is very easy to implement the transfer matrix method or the electrical circuit. Any one of them is going to be just as fine. The transfer matrix method though is what I will recommend in this course. Okay. So, next, in the next example we will put a damper. So, let us consider an assembly. Till now we were looking at assemblies which were in series. Okay. Now, we will look at assemblies which are in parallel. We will consider a spring and a mass, spring and a damper which are connected in parallel, right. Please note carefully, by this arrangement what is suggested is that the left end of the spring and the damper are having identical position. The right end of the spring and the damper is having identical position. So, they are locked because this plate or whatever you call it is a rigid plate, right. So, what I will do is that I will call as usual this as station 2 and this as station 1. Okay. So, at this station 2, the V of the spring is equals to the V of this damper. Similarly, at this station 2, the V of the spring is equals to the V of the damper, right. So, at both these stations, the spring element and the damping element have got the same motion, which means that kinematically they are equivalent, right. But will the forces on the spring, will the spring force and the damping force be same? Not necessarily, right. So, the total force that comes here, let us call this as F2 I will call this, and I will call this as F1. Okay. So, we need to calculate F2 and F1. The point is this, the total force that you are putting in at the input of this assembly is getting divided into two parts, one in the spring, the other in the damper, right. So, as a result, if you take the free body diagram at station 2, what will you see? You will see that there is a force F2 and there is a spring force resisting it, there is also a damping force which is resisting it. At station 1, what will you see with the free body diagram? You will see that there is a spring force which is actually the same as what we have written in the left end. So, the spring force and the damping force here will be resisting the force F1, right. But we need to relate F2 V2 where V2 is the velocity of this input port and V1 is the velocity of this output port. So, what we need is a transfer matrix which relates F2 V2 to F1 V1, right. So, this transfer matrix needs to be found, right. What we have realized that thus far is V2 is equals to Vs2 is equals to Vd2, which is the velocity of the spring at station 2 and velocity of the damper at station 2. The 2 points have identical motion. Similarly, V1 is Vs1 is equals to Vd1, right. This much is known that there is no ambiguity in the velocities between the spring elements and the damping elements, but as far as the forces are concerned, there can be a little issue. So, F2 is equals to Fs2 plus Fd2, right, and also F1 is equals to Fs1 plus Fd1, right. Now, please note that Fs and Fs2 and Fs1 are same. This is Fs2 Fd2 and this is Fs1 Fd1, right. So, we understand that for a spring element, the input and the output port of the spring element are at the same force. The forces cannot change between the input and the output of the spring element as well as for the damping element. That is what we did in the first lecture, where we looked at individual elements. So, Fs1 must be equal to Fs2 and Fd1 must be equals to Fd2, right. So, this is because the spring for spring and damping element the force is transmitted. Okay. Just it will be completely transmitted. So, this in turn means this implies that Fs1 plus Fd1 must be equals to Fs2 plus Fd2, which means F1 must be equals to F2, right. So, F1 must be equals to F2, that suggests that this the electrical circuit associated with this element is possibly in the shunt position, it is not in the inline position. But to verify or to confirm that it is indeed in the shunt position, you have to still verify that whether the velocities at the two stations in that is the inlet and the outlet, whether they are same or different. There is no restriction that V1 has got to be equals to V2, right. So, in general V1 is not equals to V2, right. So, therefore, V1 not being equal to V2, but F1 being equal to F2, that suggests that whatever is the electrical circuit associated with this element must go in the shunt position, right. So, this suggests the following electrical circuit. So, there has to be some equivalent impedance sitting here. There is F1 on one side, there is F2 on the other side, this is the ground line. So, F1 will be equal to F2, but V1 will be different from V2 because there is an impedance which is in the parallel or in the shunt position. So, some part of the current will go in the parallel path, leading to a difference in the current in the input side and the output side, right. So, the question is what will be this ZE. So, towards that end we realize that Fs2 or simply Fs, because Fs1 is equals to Fs2, we could as well say Fs1 is equals to Fs2 is equals to Fs and Fd1 is equals to Fd2 is equals to Fd. We already know that Fs is equals to Zs times V2 minus V1, right, delta V. We also know that Fd is Zd times V2 minus V1. Remember V2 and V1 are same for both the spring element as well as damping element. So, no need of putting separate subscripts. We already have this relation that the force that is getting transmitted by the spring is related to the impedance of the spring multiplied by the relative velocity between the input and the output, right. Same with the damper. So, these two relations now suggest that F, which is equals to Fs plus Fd, must be equal to Zs plus Zd into delta V, right. So, this means that this Zd basically is Zs plus Zd. To draw the picture in its final form, what we should have is this: the Z equivalent comprises of one Zs and one Zd. This is the ground line, this is the voltage F2, this is the voltage F1. So, what happens here is that V2 current is going in, but only V1 current is coming out, the rest of it which is delta V. So, this delta V is going to be V2 minus V1, and this delta V multiplied by Zs is going to create the first potential. Delta V into Zs plus delta V into Zd is the total potential difference that will happen in this line, which must be same as F2 and F1. This is exactly what you have. Okay. This is exactly what is what we have in this relation, where we said F is equals to Zs plus Zd into delta F into delta V. So, this F is basically the same as F2 and F1, because anyway in this situation we are seeing that the input and the output force is just the same, right. And what will be the transfer matrix associated with this system? Transfer matrix will be F2 V2 has got to be related to F1 V1, right. F2 has to be equal to F1. So, the top row of this transfer matrix is trivial 1 0. What about the bottom row? The bottom row needs to have a capture the relation that V2 minus V1 has got to be Zs plus V2 minus F which is if I just copy and paste this relation, this is the relation that we had. So, therefore, we also know that F is the same as F2 or F1. So, F2 equals to F1 is equals to Zs plus Zd times delta V, right. So, F1 by Zs plus Zd must be equals to delta V, which is V2 minus V1, right. So, therefore, V2 minus V1 has got to be, or F1. So, V2 has got to be F1 divided by Zs plus Zd plus V1. We could write this up in this matrix form by noting that this element will be 1 and this element will be 1 by Zs plus Zd, right. So, a spring damper combination element is almost the same as a spring element, except for the fact that the spring element will have an impedance Zs, the spring damper combination will have a impedance of Zs plus Zd, both in the shunt position, right. And now what you will see is that the impedance of, now if you put this together with a mass. So, now let us consider this as example 4. So, we will have a mass and then we will have that combination element which is a spring and a damper, or maybe I will draw this in a little better way. So, this is the spring damper combination element that we have derived in the last page, and this is now connected with a mass. Okay. This is K and this is C. This is our good old vibrating system, which is the first starting point of theory of vibration. Okay. So, now what we have understood is that for this part, this spring damper system, we have been able to find the analogous electrical circuit, which suggests that there has to be a spring element and a damping element in the shunt position. Okay. And the output of this combination element must not carry any current, right. So, therefore, this has to be left open. So, this part is an open circuit. We are not going to close this, this is not going to get closed, right. And what is the upstream element? The upstream element is that of a mass which is placed in line, right, and this is the ground and this is the ground. So, as well we might join these two, and since the entire force has got to be transmitted between the mass and the combination element, mark my usage of the word, I am not saying the entire force from the mass is getting transmitted to the spring element or to the damping element, it is getting transmitted to the combination element which combines both spring and damper as given by that green block, right. So, if the force has got to be transmitted, this line can as well be joined. So, therefore, there is no potential difference basically between the output of the mass port and the input of the combination port, right. And finally, if this mass is getting to see a force F, that can be accounted for by saying that there is a force, there is a voltage with respect to the ground. This is the electrical circuit associated with the spring mass damper element, but please note the spring and the damper are in parallel in the mechanical assemblage. It is turning out that spring mass damper everything is in series in the electrical circuit. Do not get confused about this series parallel business, look at it from first principles and you will be able to argue. Please understand that fundamentally the spring and the damping element should come in the shunt position. The fallacy happens because this shunt position is left open on its other end, right. Because it is being left open in the other end, you are able to interpret this circuit where the spring, mass and the damping element are actually in series, right. But fundamentally it is that the spring and the damping element are in shunt with respect to the mass, right. So, now what you see here is that the effective impedance of this circuit ZE is going to be Zm plus Zs plus Zd. What is Zm? J omega m. What is Zs? Plus Zs we have evaluated as where was that? K by j omega. So, this was k by j omega and Zd was r, right. K by j omega could be written as minus j. So, I could write k by j omega as minus j square k, or why am I using j, sorry I should use I. This is k by I omega. So, this k by I omega could be written as I square with a minus sign, minus I square is just plus 1. So, no issues if I write a minus I square. So, minus I square k by I omega and this in turn is minus I k by omega, right. So, therefore, I would write this as I omega m minus I k by omega plus r, and eventually it is capital small c, sorry, Zd is small c, right. So, then I could as well take this I of an omega m minus k by omega plus c. So, this is the equivalent impedance. This is the imaginary part of the equivalent impedance which is called as reactance, and this is the real part of it which is called the resistance. Okay. And what you see is that the undamped natural frequency is obtained when the reactance is set to 0. So, if reactance equals to 0, then omega equals to undamped natural frequency. Which is square root k by m. Okay. I think we will leave it here. We will take up a few more complicated examples maybe next class. Okay. After this we will use the same analogy to look at acoustic resonators, Helmholtz resonators, which are very important. These are lumped acoustic elements. So, using this analogy it will be very simple to introduce that idea.